In electronics now, let's write the next subheading: transformers. Electronics now, write the next subheading: transformers. Under that, please write: a transformer is a device. A transformer is a device which is used. A transformer is a device which is used to increase and decrease. A transformer is a device which is used to increase and decrease. Which is used to increase and decrease. Which is used to increase and decrease alternative voltages. A transformer is a device which is used to increase and decrease alternative voltages. Isn't it? A transformer has two coils. This is a coil. How many such coils are there? There are two such coils are there. They are wound on the same metal core. Means a metal core means something, let's say that's a metal rod. On the metal rod, they have wound this coil like that. Okay? Describe, start point and write. A transformer has two separate coils. A transformer has two separate coils. A transformer has two separate coils, which are wound on the same core, C-O-R-E. A transformer has two separate coils, which are wound on the same core. Right, a coil is a wire, it is wound on something. We learn everything about transformers under electromagnetism lesson, under magnetic field lesson. Here I am just giving you the brief description. A transformer has two coils. They are wound on the same coil. A transformer can increase and decrease alternative voltages. That's all we learn under this. And here we will give you the circuit symbol also. But we learn almost all the things about transformers in our magnetic field lesson. Start point and write. The circuit symbol of a transformer is given below. The circuit symbol of a transformer is given below. The circuit symbol of a transformer is given below. Look at board there. So this is the first coil. Look at board. This is the second coil. And core is indicated by these two lines. This coil is, the first coil is said to be the primary coil. What's the name there? Primary coil. This is said secondary coil. Secondary coil. If the current in the primary coil is I1, the current in the secondary coil I2. Input voltage, voltage in the primary coil V1, output voltage, voltage in secondary coil V2. The number of turns in the primary coil N1, number of turns in the secondary coil N2. Turns mean you take the wire and take one cycle. So how many turns here? Only one turn. Now how many turns? 1, 2. Now how many turns? 3, and so on. Got it? Draw this figure quick. Is right. The relationship between input and output voltages. The relationship between input and output voltages. The relationship between input and output voltages can be found by the following equation. The relationship between input and output voltages can be found by the following equation. No need to prove the equation, you just want to remember. V1 over V2 equals N1 over N2. V1 over V2 equals N1 over N2. We should write what's the N1, what's the N2. To write them. Please write simple N1 equals number of turns in the primary coil in one equation mark, number of turns in the primary coil in 2 equals number of turns in the secondary coil in 1 equals number of turns in the primary coil, in 2 equals number of turns in the secondary coil, number of turns in the secondary coil. Okay, yeah. Star point and right. If there is no loss in energy, if there is no loss in energy, if there is no loss in energy, comma, the following relationship can be written. If there is no loss in energy, comma, the following relationship can be written. The following relationship can be written. What's it there? So actually there are losses in energy transformers. Theoretically, we believe that no losses in energy. We can't make any instrument where there are no energy losses. But theoretically, we believe in advanced level physics, we believe there is no loss in energy. Therefore, we can write input energy or input power. Why can we write even input power here? Power is also energy. The only difference is energy per unit time. So energy per unit time means energy generated per 1 second. So input energy or input power should be equal to the output power or output energy. So input energy can be found by the equation VIT, V1 I1T, output energy means V2 I2 times T, VIT. Look at board here. So I can take the V2 to this side and I1 to the, so I'll take only V2 to this side. Then what are the terms remaining here? V1 over V2. I have taken V2 to this side. Into I1 into T. Here I2 into T. And now what will happen to these terms T and T here? The terms T terms are cancelled out. What is V1 over V2? Lawan? V1 over V2 is N1 over N2. In the place of V1 over V2, I can write N1 over N2 into I1. T and T cancelled out. Here I have I2. Now I can take N2 to this side. Then I will obtain the final equation as N1 I1 equals N2 I2. N2 I2. That's it. Complete. Right. So that's it. There are two separate coils wound on the same metal core. The relationship between input and output voltage is given by this equation. The relationship between input and output current given by this. N1, N2 are number of turns. One more thing. What's it? Star point and 3 star points and right. If a transformer increases the voltage, if a transformer increases the voltage, come on, it is known as, if a transformer increases the voltage, come on, it's known as, look at what, it's known as step up transformer. It's known as a step up transformer. Step up transformer. Same point. If a transformer decreases, the voltage, if a transformer decreases the voltage, come on, it's known as a, look at both and right, step down transformer. It's known as a step down transformer. If a transformer decreases the voltage, it's known as a step down transformer. Underline the words step up, step down. Let's write an example. A generator generates an alternative voltage of, a generator generates an alternative voltage of, look at what, 660 volt, 660 volt, 660 volt. We'll stop. A transformer is used. A transformer is used to increase the voltage up to 33,000 volt. 33,000 volt. A transformer is used to increase the voltage up to 33,000 volt. We'll stop. There are 400 turns. In the primary coil. There are 400 turns in the primary coil. There are 300 turns in the primary coil. We'll stop. How many turns should be there in the secondary coil? How many turns should be there in the secondary coil? How many turns should be there in the secondary coil? Right. So this is the real thing. This is the real situation happens in a power station. Listen to me, dear. There are power stations in Sri Lanka, Noracholi, the coal power station, and there are some diesel power stations, Yugadanavi, like that. So in power stations, they generate a smaller voltage. It does not generate, a generator cannot generate 33,000 volts like that, 132,000 volts. It generates a smaller voltage like 660 volts. So the generator can be indicated by this symbol, a voltage source. It generates a voltage of 660 volt. Actually, even we draw arrows, you know that alternating voltages, it does not have an exact direction. Even we have marked the directions, actual directions are always changed. Don't worry about it. So it is said that there are 400 turns in the primary coil. The question asks us find how many turns should be there in the secondary coil. The secondary coil voltage is given as 33,000 volt. So these are the given data. So this is the generator. This is the generator. Right? Draw this figure in. Draw the figure and mark the given data. So we can directly use the equation here. No need to prove any equations. We can directly use the equation like this. V1 over V2 equals N1 over N2. V1 is 660, V2 is 33,000. N1 is 400. The question asks what the N2 is. So we can easily cancel out this 0 and this 0. 66 divided by 33 is 2. 33 divided by 33 is 1, and with the two zeros 100. Equal 400 divided by N2. So I can take N2 to this side and 2 and 100 to the other sides by cross multiplication. So N2 equals 100 divided by 2. 100 goes up, 2 goes there. Into 400. So we can easily divide 400 by 2. What is 400 divided by 2? Now 200 and with the two zeros. So how many turns are there? 200 into 100. 1, 2, 3, 4 zeros. It means 20,000 turns. Number of turns in the secondary coil should be 20,000. Who got this answer? Right, that's it. Complete. Right. In electricity board, they use several transformers, not only a single transformer, but many transformers. Look at board here. Right. A generator generates a smaller voltage. A generator generates a smaller voltage, something like 660 volts, something like this. So in this case, what is the generated voltage here? Supply voltage is 660 volts. Then the first transformer, increases this voltage up to 33,000 volt. So what kind of a transformer is this here? Step up transformer or a step down transformer? Step up transformer, voltage increases. Then there will be another transformer like this, right? This transformer, normally this 33,000 voltage reduces to 11,000 volt. So what kind of transformer is this? Step up or step down? Step up. So number of turns here, let me take number of turns here as 1,000 turns. 1,000 turns. So we don't know the number of turns in this transformer. Let me take this transformer as T2. Let me take this as T1. But can we use 11,000 volts at our home? So in our houses we can't use. Therefore, this voltage reaches to a village or a town. There will be another transformer. This transformer reduces this 11,000 volt into 230 volt. Can you understand? Right. So here we don't know the number of turns in the secondary coil in T2. Right. So this is the T3 transformer. Let me take, there are 500 turns in the primary coil of T3 transformer. Please write example number 2. sample number 2. The following diagram shows the following diagram shows a combination of transformers. The following diagram shows a combination of transformers. Used to provide electricity. Used to provide electricity. Used to provide electricity. The following diagram shows combination of transformers that are used to provide electricity. Continue. Find the number of turns in the secondary coils. Find the number of turns in the secondary coils. Number of turns in the secondary coils of T2 and T3 transformers. Find the number of turns in the secondary coils in T2 and T3 transformers. T2 and T3 transformers. Draw this figure here. Find the number of turns in T2 and T3. Find the number of turns of the secondary coils of T2 and T3 transformers. First, you draw the figure here. Quick. So we can apply this equation, voltage equation, to the two transformers separately. To the T2 transformer, I can apply this equation. V1 means this voltage. What should be this voltage? If this is 33,000, the potential difference between these two wires should be 33,000. Therefore, input voltage at primary coil of the T2 transformer is 33,000 volts. V1 is 33,000 divided by our V2, that is 11,000 voltage. It is given in the picture. 11,000 voltage is given in the picture. N1 is given as 1,000. We want to find N2 of the second T2 transformer. 33,000 divided by 11,000 is 3. Therefore, this is 1,000 divided by N2 is 3. If I use cross multiplication like this, the number of turns in the secondary coil of the T2 transformer is 1,000 divided by 3. Who got this answer? That's it. So let's apply the same equation to the other transform. For the T3 transform also, let's apply the same equation. V1 over V2 equals N1 over N2. For the third transformer, the input voltage should be 11,000. You see that 11,000 is directly given to the second transformer, third transformer. So input voltage of the primary coil, voltage across the primary coil of the T3 transformer is 11,000 divided by V2 equals N1 is 500. The question asks us to find what the N2 is. What is V2? V2 is also not. V2 is 230. V2 is 230. Can we find N2 of the third transformer right here? We can cancel out the two zeros. And we can cancel out these two zeros also. After that, let's use cross multiplications. So then what is N2 then? N2 equals 23 goes up, 110 goes down, and 50 will be there. Am I right there? Goes up, goes down. Now again we can cancel out these two zeros. 3 times 5, 15. 5 times 2, 10, with the remaining one, 11. Divided by, that's it, 115 over 11 turns. But in the exam, you should divide this and should give the answer at least with 2 decimal places. Who got this answer? Now, if you divide this, you will get about 10.45 turns. 10.45 turns mean about 10 turns. 10 turns, 10 to 11 turns. Let's discuss one more example, right? In day-to-day life, we use transformers like this. Normally, house voltage supply is 230 volt, right? We use the transformer and we reduces this voltage normally to 12 volt. So this 12 volt is given to these are alternative voltages. These all of them are alternative voltages. This 12 volt is then converted into DC by using a full wave rectifier, right? This 12 volt is then converted to DC by using uh, full wave rectifier circuit, right? So such a combination, a transformer, full wave rectifier combination, a capacitor, safety diode, Zener diode, all these combination, all of that combination is known as a power pack. What's the name given here? Day-to-day life, we call it as a power pack. Let's discuss one more example for a power pack here. So this voltage is 230 volt. Let me take this current as 0.2 milliampere. 0.2 milliampere like this. So we want to find this voltage and current I. Number of turns in the primary coil. Let me take it as 100 turns. Please write. Please write. The transformer in a power pack. The transformer in a power pack, the transformer in a power pack has, the transformer in a power pack has 100 turns in its primary coil. The transformer in a power pack has 100 turns in its primary coil. In its primary coil. Full stop. It reduces a 230 volt. It reduces a 230 volt to a 12 volt. To a 12 volt. Full stop. The current in the primary coil is 0.2 milliampere. The current in the primary coil is 0.2 milliampere. 0.2 milliampere. Roman number 1. How many turns should be there in the secondary coil? Roman number 1. How many turns should be in the secondary coil? How many turns should be in the secondary coil? Roman number 2. Find the output current of the transformer. Find the output current of the transformer. Right, draw this figure here. Draw this figure, the transformer figure. we can easily find the number of turns in the secondary coil by applying the equation V1 over V2 equals N1 over N2. Right, so let's apply the equation V1 over V2 equals N1 over N2. V1 230, V2 12 volt, N1 is 100, N2 just use cross multiplication to interchange the terms. So you get N2 equals 12 divided by 230. 12 divided by 230 into 100. Now one of the zeros can be cancelled out. One of the zeros can be cancelled out. So what are the remaining numbers there? N2 equals 12 into 10, 120 divided by 23. So this much of turns are there. Shall we divide and find it? Who got the answer up to this level as a fraction? Let's divide and find. Let's divide this. If you divide it, you will get 5.2. It means only 5 turns are there. So what does it mean here? The side here, what is the voltage here? 12. Smaller voltage, smaller number of turns. Can you identify it? Here 230, larger voltage, larger number of turns, 100 turns. 230, 100, larger voltage, larger number of turns. 12 volt, smaller voltage, smaller number of turns. So you should remember, if a coil has a smaller voltage at one side, that side has a smaller number of turns. You must remember it. Clear? So it's a step down, listen to me. This is a step down transformer. It reduces the voltage. Therefore, secondary coil has a smaller voltage. Therefore, secondary coil has a smaller number of turns. So in the examination, they will ask the number of turns in the secondary coil of a step down transformer is smaller. Correct or wrong here? Correct. Step down transformer has smaller voltage in the secondary coil. Smaller voltage in the secondary coil means smaller number of turns in the secondary coil. Clear? Therefore, step down transformer has smaller number of turns in the secondary coil. Got it? Completed. Then how do you find the current? How do you find the current? In Roman number 2, it is asked us to find the current. N1 I1 equals N2 I2. N1 number of turns in the primary coil 100. I1 current in the primary coil 0.2 milliampere. N2 we should use the fraction. We should use the fraction because this is not exactly 5.2. So let's use the fraction. 120 divided by 23 into I2. So as I1 is in milliampere, I2 will also be in milliampere. Find I2 here, right? What about the current? I can use cross multiplication to inject cross multiplication. Yeah. Remember, 100 0.2 can be written as 2/10 milliampere into 120 divided by 23 equals I2. Now what will happen? I can cancel out this 0 and this 0 can be cancelled out. 12 times 2, 24, 24 times 100 here. 12 times 2, 24, 24 times 100, 2400. Divided by 23 unit is milliampere. Who got the answer up to this level? Right. I2 here. Shall we divide this? That's a small mistake. 23 should come up, 120 should go down. 23 should come up, 120 should be there. That's a mistake. Then 23 times 2, you can this 0. 23 times 2, Lamai. 23 times 2, 26. Sorry, not 26, 46. Wait. What about the denominator? 23 times 2, 46. The denominator, these two zeros can be cancelled out with these two zeros. And divided by 12 will be there. Who got the answer up to this level? Sorry, I made a mistake. Who got the answer up to this level? Right. Now, what will happen if we divide 46 by 12? If we divide 46 by 12, 3.8. The current is 3.8 milliampere approximately. You got the answer even up to this level? Right, very good. Complete. We can learn several things from this example. Remember? From a step-down transformer, reduces the voltage 230 volts to 12 volts. The voltage is reduced. But what about the current here? Input current 0.2 milliampere, output current 3.8 milliampere. So it means output current is increased. We'll write it as a note. These things are in MCQ, so you should remember this fact. Put number 1, 2, 3 and write number 1. A step-down transformer. A step-down transformer. A step-down transformer reduces the output voltage. Reduces the voltage and step down transformer reduces the voltage and increases the current. A step down transformer reduces the voltage and increases the current. Number 2. The primary coil has more turns. The primary coil has more turns. The primary coil has more turns. Within brackets, in a step down transformer, the primary coil has more turns. We'll stop within brackets. In a step down transformer, okay dear? Right. So you should remember this point. A transformer, if a transformer reduces the voltage, it increases the current. Transformer reduces 230 volt to 12 volt. Current increases from 0.2 to 3.8. If voltage is reduced, current is increased. What is the inverse logic? If voltage is increased, current is reduced. Clear? Star point and right. Similarly, star point, not 1, 2, star point. Similarly, if a transformer increases the voltage, within brackets, step up. If a transformer increases the voltage, within brackets, step up. It reduces the current. It reduces the current. Clear? Right. Now we have learned a lot of things, so we can discuss a past paper question. No need to write the question because I have already given you a tube. Let me select one. Let's try for 2013 electronic essay question. 2013 electronic essay question. Write the heading 2013 AL electronic essay question. No need to write the question. Let me read it. A step down transformer. A step down transformer produces an output voltage of 18 volt. Peak value means maximum value. 18 volt from 240 volt 50 hertz AC mains voltage. 240 volt 50 hertz AC mains means the normal electricity voltage that we use at our houses. In our homes, we use 240 volt AC voltage supply. 50 hertz means 50 cycles are completed for 1 second. I have taught you positive negative half cycles. Do you remember? I have taught positive negative half cycles in theory class. So there are 50 such cycles. Simple equation. Draw a circuit diagram of a bridge rectifier connected to the appropriate terminals of the above transformer. Right. So what is the circuit symbol of a transformer here? So this is the circuit symbol of a transformer. A step down transformer means it reduces the voltage. We give a voltage of 240 volt. The transformer reduces this voltage to 18 volts. So we should identify that 240 is the maximum supply voltage, 18 volt is the maximum output voltage of the transformer. Now, these two wires are connected to a bridge rectifier. Bridge rectifier means full wave rectifier circuit. Can you do the full wave rectifier circuit here? Try it here. And read the rest of the question. Check whether they have asked you to do capacitors, Zener diodes, safety resistors. Read the rest of the question because you need some more space here to draw Zener diodes and capacitors if it is asked. I don't know. Read the question and draw it. Start. So if you read the rest of the question, they have asked all the other components that should be connected in a rectifier circuit. So if you draw only the full wave rectifier, there should only be 4 diodes. That's so simple. How the diodes are connected here? The first 2 diodes are connected such a way that face to face of this diode to the face of the other diode. That's how we remember. There is no face and back of a diode. How do we remember? The method we use to remember, face to face. The next 2 diodes are connected such a way that back to back. That's how we connect. Back to back, face to face. Then output is taken from face to face point, back to back point. How do we take the output there? Output is taken face to face and back to back. So in the next question, they ask us to draw several graphs. So I'll mark this point as these 2 points as A and B. So output of the full wave rectifier circuit is AB, right? Then we connect a smoothing capacitor. C is the smoothing capacitor. If you read the rest of the picture, you will find, right? Let's say C1 is the smoothing capacitor, right? Then let me name these 2 points C and D. CD is the output voltage with the capacitor. Then we should connect the safety resistor RS. Then we connect Zener diode, reverse bias Zener diode. Finally, the output resistor, the load resistor RL, right? A, B, C, D. If I want, I can name them as EF, and these are GH. The center voltage is VZ. VZ is directly given to R. So this is a complete full wave rectifier circuit with the smoothing capacitor and the Zener diode. If you read the rest of the question, they have asked you to include the capacitor and the Zener diode also. Who has drawn the circuit properly, correctly, complete it. The next question. What is the next question? Then simple B. Draw the voltage waveforms. Draw the voltage waveforms across a resistor connected across the output at the following output stages. We should draw the output voltages under these conditions. What are the conditions here? Transformer output. Roman number 2, rectifier output without the smoothing capacitor. Roman number 3, rectifier output with the smoothing capacitor. Show you a capacitor connection in the circuit that you have drawn above. So that's why I have asked you to read the entire question before you draw this figure. What is the transformer output here? B Roman number 1. The transformer output voltage will be like this. You should draw several curves. 1, 2, 3, 4, 5. At least you should draw 6 such curves. This is T measured in seconds. Where transformer output maximum voltage is given as 80. So this is the transformer output. So simple. 18 volts. It's an alternating volt. So it changes between plus 18 and minus 18. It's better if you produce these dotted lines. But here in the examination, they have given full marks even if you have not marked this 18. Even if you have not marked this 18, they have given the full marks. But I would like if you draw the dotted lines, mark plus 18 and minus 18. B Roman number 1. B Roman number 2, rectifier output without the smoothing capacitor. What will be the rectifier output? Rectifier means the 4 diodes, the combination of 4 diodes, that is known as rectifier. So what will be the rectifier output voltage without the smoothing capacitor? B Roman number 2, without the capacitor. Look at both. So this is B measured in volt. This is T measured in seconds. The rectifier converts the entire signaling, entire alternating voltage into a direct current voltage. So rectifier output voltage will be like this. So in this case, don't worry about the junction voltages. You can assume that the diodes are ideal. By assuming the diodes are ideal, they don't ask anything about the junction voltage and that kind of things. Just draw the wave pattern like this. That's it. B Roman number 3. Rectifier output voltage with the smoothing capacitor. With the smoothing capacitor, then what will happen is B Roman number 3 with the smoothing capacitor. With the smoothing capacitor. Look at board here. So this is the time measured in seconds. You must mark the units properly, otherwise no marks will be given. This is V measured in volt. Measured in volt. Look at board here. When the smoothing capacitor is used, look at board. Without the smoothing capacitor, output voltage will be like this. Without the smoothing capacitor, output voltage will be like this. Am I right here? This is what without the smoothing capacitor. But once the smoothing capacitor is used, when the voltage going to be reduced, the capacitor gives a voltage. Therefore, this part is cancelled. Can you understand it? So there will be a straight line graph. Again, when the voltage is going to reduce, the capacitor gives a voltage, then there is no voltage drop like this. That's what happens when a capacitor is connected. When again voltage is going to drop, capacitor gives a voltage like this. Right? So same here, there will be a straight line voltage like this. So a curve, straight line, a curve, straight line, a curve, straight line, a curve, straight line, and so on. Complete here? The next question, Roman number 4. Output after connecting a zener diode to regulate the voltage. So show the zener diode connection in the circuit that you have drawn. So you should draw the zener diode connection also. That is Roman number 4. So what will be the output voltage once we connect a zener diode? Now, have they given the zener diode voltage? Eh? After the zener diode is connected, this is the time measured in seconds. This is the output voltage. Unit is volt. After the zener diode is connected, we will obtain a constant straight line voltage. It is horizontal. Constant output voltage can be obtained after the zener diode is connected. Right? See Roman number 1. What is the advantage of choosing a large capacitor value for the smoothing capacitor than a smaller value? See Roman number 1. They ask why it is better to use a capacitor having a larger capacitance. If you use a larger capacitance, this straight line part will be something like this. The drop will be highly reduced. Can you understand? That's the drop. If you use a capacitor with a larger capacitance, so it means you will almost obtain a straight line voltage if you use a capacitor with a larger capacitance. That's what, right? So it means the variation of the output voltage here. What was the earlier variation? Let's say this is 17, this is 15. Output voltage reduced in between 17 and 15. Now output voltage is reduced between 16.9 and 17. Maximum 17, minimum 17, 16.9. So the variation of the output voltage is reduced when we use a capacitor with the larger capacitance. Capacitance is made in measured in farad. You will learn about capacitors in electric field lesson. Right. Which write C Roman number 1. When a capacitor with a larger capacitance is used, when a capacitor with a larger capacitance is used, when a capacitor with a larger capacitance is used, the variations of the output voltage is reduced. the variations of the output voltage is reduced. Then the output voltage will be more linear. Then the output voltage will be more linear. Okay. Variations of the output voltage is reduced. Full stop. Then the output voltage will be more linear. Okay, dear. See Roman number 2. When the smoothing capacitor is in place, what is the maximum reverse bias voltage that can appear across a diode? There is the smoothing capacitor is there. What will be the maximum reverse bias voltage of any diode? During the positive half cycle, which diodes conduct electricity here? Naman? You don't remember. Very good, nice. During the positive half cycle, D1, D2 diodes conducts, you know that point. The transformer gives a voltage of 18 volt. Then D1 diodes, what is the reverse bias? What is the forward bias junction voltage of a normal silicon diode? 0.7. For a germanium diode, 0.3. But in this question, it is given that the junction voltage is 1 volt. So how many volts here? 1 volt. 18 is given. So what is the voltage here? This diode will reduce its junction voltage. So this will be 17 volt. Am I right? This point is normally connected to the ground. So this is ground mean. What is the voltage here? 0. Am I right? 0, 18, this point 18, this diode reduce 1 volt by the junction voltage. This is forward bias, this is reverse bias. So voltage here 17, as this point normally connected to the ground, this is 0. 17 and 0. So what is the voltage across this reverse bias diode? 17 volt. Got it here? Please write. I'll give you this note also. Please write. Answer 17 volt. 17 volt. 17 volt. Please write not. We will need this figure to understand the answer. We will need this figure to understand the answer. Not. The circuit is equivalent to the following circuit. The above circuit is equivalent to the following circuit. The above circuit is equivalent to the following circuit during the positive half cycles. 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 Draw this figure in. So then you can understand the answer. How 17 voltage came. So you can understand. Right? Right. Whenever that happens. D. D. If the center diode, if the center diode, if the center diode above has the following specifications, and here අපි ගත්ත center diode එකේ the center diode has the following specifications. මොනවාද? Calculate the value of the safety resistor that has to be used in order to safeguard the center diode. Center voltage 10 volt. So we have to calculate this. Let's listen here. This is the safety resistor. I think we have already drawn it. No need to draw it again. And this is the center diode. This is the center diode. What is this voltage here? Center voltage is 10 volt. No need to draw a separate figure. Even here you can mark. Even here you can mark. This is the center voltage. V is the 10 volt. The maximum permissible current for the center diode 200 milliampere. 200 milliampere. So a current of 200 milliampere. The maximum current 200 milliampere go through this diode and coming through this one. Maximum possible current, maximum permissible current is 200 milliampere. So please mark these things on the same figure here, on this figure. It's okay. So we want to find the value of Rs. That's it. We want to find the value of Rs. Mark them on the same figure, on the previous figure. Now I am going to ask you a very important question. Listen to me carefully. Listen to me carefully. Let me mark this voltage as VCD. Mark it. VCD is the potential difference across the capacitor. Mark it. What is this voltage? 18. When 18 flows through this diode, it reduces 1 volt. So what is the voltage here? 17. And if you go again like this D2 also reduces 1 volt. Can you understand? So 18 is the maximum voltage. This will reduce 1 volt. Or I can write 18 should be equal to this 1 volt plus VCD plus this 1 volt. Let's write like that. Supply voltage equal to VCD plus like this. Can you understand? 1 volt VCD plus this 1 volt equals to 18. Can you understand it? That's the question I'm going to ask. Check whether you can understand it. If not, please ask. This 18 volt is the voltage given out by the rectifier, sorry, the transformer. During the positive half cycles, D1, D2 forward bias, D3, D4 reverse bias. Therefore, no current flows to D3, D4. So I can erase them. So I can erase. Why did I erase D3, D4? Because no current flow through D3 and D4. They were reverse bias. Now I have removed the reverse bias diodes, so I don't worry about this reverse bias voltage. I have removed the reverse bias diodes, so I do not worry about the reverse bias voltages. Now I am going to consider the forward bias voltages. When this 18 volt is into clockwise direction, this 1 volt is into the anti-clockwise direction. When a diode is forward bias, when the current flows through the forward bias diode, it gives an oppositely directed voltage, which is known as a junction voltage. The junction voltage is given in the equation as 1 volt. Now, the supply voltage is into clockwise direction. This 1 volt is into anti-clockwise direction. Even this VCD is into anti-clockwise direction. Am I right? Supply voltage into clockwise direction, VCD, and this junction voltage 1 volt into anti-clockwise direction. What about this one here? This also into the anti-clockwise direction. Clear? So what are the voltages into the anti-clockwise direction? You have to rotate it and check. Yeah. You should rotate the diode and check. So there are 3 voltages into the anti-clockwise direction. 1 volt, VCD, 1 volt. Clockwise direction 18. So voltage into clockwise direction should be equal to the voltages into the anti-clockwise direction. That's what I have written here. Okay. So 18 should be equal to 1 plus VCD plus 1. These 3 voltages into clockwise direction, 18 is into anti-clockwise direction. So 18 equals 1 plus 1, 2 plus VCD. If you take 2 to this side, it will come this side as minus 2. That is VCD. Therefore, VCD equals 16 volt. Actually, VCD is the output voltage of the rectifier circuit. Output voltage is the full wave rectifier circuit. If you do not understand any of these things, let's say you don't understand clockwise story, you don't understand any of these things, then the easiest way to remember is in the full wave rectifier circuit, output voltage is equal to input voltage minus the forward bias voltages of the 2 forward bias diodes. If you do not understand any of these things, what is the easiest way to remember? Output voltage VCD equals to supply voltage AB minus junction voltage of the first forward bias diode minus junction voltage of the second forward bias diode. 1 volt, 1 volt, 2 volt, 18 minus 2 is 16. That's the other way to remember. So use any of the methods, try to identify that VCD is 16. Right then? Now it's very simple. So when we find the safety resistance, there should not be a load connected here. When we calculate the safety resistor for a Zener diode, only the Zener diode should be there. The other part should not be here. All of them should be removed. Right? Safety means working without all the other things. It means the entire current should flow through the Zener diode. I have explained that part very well in our theory class. Right? So nothing should be connected here. Only the Zener diode, only the safety resistor and the supply voltage. So potential at this point 16, potential at this point 10 volt. Now what is the potential difference across RS resistor here? Potential difference. Potential difference across RS resistor. Potential difference across RS resistor. Potential at this point, that's what we have found as BCD 16. Potential across the Zener diode is 10 volt. The breaking voltage of a Zener diode, when it is reverse biased, is said to be the Zener voltage, that is given as 10. 16 minus 10 is 6 volt. So after you have found the potential difference across RS resistor, apply Ohm's law. For the RS resistor, apply Ohm's law. Potential difference across RS resistor 6. Current is given as 200 milliampere. To convert milliampere into ampere, we should divide it by 1000 into the same resistance is RS. Can you do the rest and find RS here? Start. Right. Here we can cancel it out like this. This is 6. 200 divided by 201. 1000 divided by 200 is 5 into RS. Just take 5 this side. 6 times 5 equals RS. Therefore, RS is 6 times 5 is 30. RS is 30 ohm. You got this answer? So safety resistance is 30 ohm. So when you calculate the safety resistor, you should consider that all the current flows through the Zener diode. And you should consider the maximum voltages, maximum currents. Even if a sinusoid is even if it is safe under the maximum currents and voltages. If a sinusoid is safe even under the maximum current and the maximum voltage, it means it is always safe under all the other currents and all the other voltages. Something is safe even we apply maximum voltage and maximum current. It means it will definitely be safe under the other currents and voltages. That's the logic. Right. What's the next question? Simple E. Simple E. A student has decided to use the rectifier circuit with the smoothing capacitor, but without the Zener regulation, as the DC power supply, which is necessary to operate a common elite amplifier. Have you asked anything before that? No, no. At once they have asked about common elite amplifier. A student has decided to use rectifier circuit with the smoothing capacitors, but without the Zener regulation. As the DC power supply, it is necessary to operate a common elite amplifier. Draw a circuit diagram of a common elite amplifier. I'll simply draw it. I'll draw it. Just look at board. It's not such a big thing. Right, listen to me here. A common elite amplifier has 4 resistors. Look at board, try to remember. 4 resistors. 2 of them are here. The other 2 are there. And there is a supply voltage source. The supply voltage normally indicated as VCC. That's how the name. Supply voltage is named as VCC. So how many resistors are there here? Listen to me carefully. It is asking you to draw. At this point is always connected to the ground, so voltage is 0. And amplifier increases the amplitude, which is given from a signal given from mic, and the output is given to a speaker. The mic is connected through a capacitor. The mic is connected through a capacitor. C1 is the capacitor. So this is the input voltage. Output is taken. Output is again given through a capacitor. This is C2. So this is V out. This is V. The next additional part is the transistor. The circuit symbol of a transistor is like this. It has some terminals said to be base, right? Emitter and collector. This emitter and collector connected to here. So this is the base terminal of the transistor. Emitter connected to here. Collector connected to here. And there is no wire. So this is said to be common emitter amplifier. The resistors are named as R1, R2. Resistor connected to the collector, RC. Resistor connected to the emitter, RE. That's all. This is known as common emitter amplifier. Right? Simple E, Roman number 1. Right, final question. E Roman number 2. State the changes that you would expect in the voltages at the base and the output of the amplifier due to the voltage variation, ripple voltage of the power supply. Now, actually this VCC should be a DC voltage. You must connect the battery here. Now, what do they do? For this amplifier, they do not connect a battery here. Without connecting a battery, the power, the voltage is given. Let me read that question again. Right? The voltage is given like this. A student has decided to use the rectifier circuit with the smoothing capacitor but without the Zener diode. Zener diode is not used. Only the capacitor is there. That voltage is given here. Can you understand? So what is the variation of the voltage without the Zener diode? Without the Zener diode, voltage was like this. Do you remember this graph? When this kind of a voltage, this circuit wants a constant voltage like this, right? But they do not give a constant voltage. Voltage with only the capacitor is given. So when these ripples, this ripple voltage provides a ripple current to the base. This is base. Then the voltage ripples are amplified by the transistor. This ripple voltage, you see that it is given to the transistor. Transistor increases this ripple voltage. Then you will hear the sound given by the mic, and you will also get a hum sound, a noise, because of these ripples. Can you understand it? We will learn a lot of things about the amplifier, but now just write the answer. Please write. What do they ask? Let me read the question at one more time. State the changes that you would expect in the voltage at the base and the output of the amplifier due to the variation of the ripples. Please write. As there is no Zener diode, in the rectifier circuit, as there is no Zener diode in the rectifier circuit, as there is no Zener diode in the rectifier circuit, the supply voltage to the amplifier, the supply voltage to the amplifier, the supply voltage to the amplifier, has some ripples, the supply voltage to the amplifier has ripples. Full stop. Those ripples voltage, those ripples voltage given to the base terminal of the transistor. Those ripple voltage is given to the base terminal of the transistor. You will line and write therefore. Base voltage is changed according to the ripples. Therefore, the base voltage is changed according to the ripples. The ripple voltage is appeared as an input signal to the base. The ripple voltage is appeared as an input signal. The ripple voltage is appeared as an input signal. Next line, next point. Finally, the ripple voltage is amplified by the transistor. Finally, ripple voltage is amplified by the transistor. Final ripple voltage is amplified by the transistor and given as the output through the collector terminal. Through the collector terminal. Okay, dear? Right. So this ripple voltage is given to the base. The base terminal will detect it as an input signal. That input ripple voltage is amplified by the transistor and given out to the collector terminal. That's it. That's what they have asked. So we have completely discussed 2013 electronic essay question. That's it.